Hey there, it's Shannon, Math Chick Myers, and today we're looking at section 3.3 from the ZIL text, which covers modeling with systems of first order differential equations. So in this section, we will again only construct models. It'll be a little work, but mostly constructing models for applications using systems of differential equations. Don't worry, we'll check out how to solve some of them in later chapters. So for linear slash nonlinear systems, a single DE can serve as a mathematical model for a single population in an environment. When there are two interacting and possibly competing species living in the same environment, then we may model their populations using a system of two first-order differential equations. So if we let x at t and y at t denote the two species, respectively, we have the system dx dt is equal to g1 at t, x, and y, and dy dt would equal to g2 at t, x, and y. When g1 and g2 are linear in the variables x and y, then we have g1 at t, x, and y equals to some linear combination of these things. So writing that as c1 times x plus c2 times y plus some f1 at t, and then g2 at t, x, and y. Continuing on with those constants, we'd have c3 times x plus some c4 times y plus some other function f at 2 at t, where the coefficients ci could depend on t. If this is all true, then the system dx dt equal to c1x plus c2y plus f1 at t and dy dt equal to c2 times x, c3 times x plus c4 times y plus f2 at t is said to be a linear system. A system of differential equations that is not linear is said to be nonlinear. So it's either linear or not. All right, radioactive series. When a substance decays by radioactivity, it usually doesn't just transmute in one step to a stable substance. It goes through a series of substances. This process is called a radioactive decay series. It continues until a stable element is reached. Suppose a radioactive series is described by X goes to some Y, and it's got this constant negative lambda 1. Then it goes to Y, and from Y to Z, it's got some negative lambda 2, where K1 equals to negative lambda 1, which is less than 0, and K2 equal to negative lambda 2, which is less than 0, are the decay constants for substances X and Y respectively, and Z is a stable element. Also, suppose that X at T and Y at X at T, Y at T, and Z at T denote amounts of substances X, Y, and Z respectively remaining at some time T. The decay of element X is described by dx dt equals to negative lambda 1 times X, and the decay of element Y, which is a net rate, is described by, well, lambda 1 times X is being added, right, from that first one. So we'd have dy dt. So lambda 1 times X is being added. But then Y is losing negative lambda 2 times Y is what it's losing. Since Y is gaining atoms from X, and at the same time losing atoms due to its own decay. Since Z is a stable element, it only gains atoms from the decay of Y. And so dz dt is going to equal to lambda 2 times Y. So if we put all this stuff together, we will have dx dt is equal to negative lambda 1 times X, dy dt is equal to lambda 1 X minus lambda 2 times Y, and dz dt is equal to lambda 2 times Y. Good so far? The chemical element potassium is a soft metal that can be found extensively throughout the Earth's crust and oceans. Although potassium occurs naturally in the form of 3 isotopes, only the isotope potassium-40, K40, is radioactive. This isotope is also unusual in that it decays by 2 different nuclear reactions. Over time, by emitting beta particles, a great percentage of an initial amount, K0, of K40 decays into the stable isotope calcium-40, whereas by electron capture, a smaller percentage of K0 decays into the stable isotope argon-40. Because the rates at which the amount C at T of calcium-40 and A at T of argon-40 increase are proportional to the amount K at T of potassium present, and the rate at which K at T decays is also proportional to K at T, we obtain the system of linear first-order equations dc dt equals lambda 1 times K, dA dt equals lambda 2 times K, and dk dt is equal to negative quantity lambda 1 plus lambda 2 end quantity times K, where lambda 1 and lambda 2 are positive constants of proportionality. So, going from the last equation in this given system, we want to find K at T if K at 0 is 0. Then we'll use that information, k at t to find a at t and c at t from the first and second equations. Good so far? Okay, so let's do this thing. So we have dk dt. I'm going to add lambda 1 plus lambda 2 times k over to this side of the equation, and it's going to equal to 0. So here, oh, and my bad, there's a typo here. This is k0. So we are needing to find an integrating factor, because this is linear in form. So to do so, we look at the coefficient in front of the k, right? And we have e to the integral of quantity lambda 1 plus lambda 2 dt. And that's just going to be e to the lambda 1 plus lambda 2 times t. So when we multiply both sides by e to the lambda 1 plus lambda 2 times t, we will have e to the lambda 1 plus lambda 2 times t dk dt plus e to the lambda 1 plus lambda 2, that quantity times t, times lambda 1 plus lambda 2 times k is going to be 0. Good so far? And now, using that trick that this sum of on the left-hand side is going to be the derivative with respect to t of e to the lambda 1 plus lambda 2 times t times k. And that, in turn, will equal to 0. And then we now want to set it up for integration. So we'll have e raised to the lambda 1 plus lambda 2 times t dk is equal to 0 dt. This is a little tricky. We'll keep the 0 dt going and integrate both sides. Now, in order to integrate the integral of the left-hand side will be e raised to the quantity lambda 1 plus lambda 2 times t times k is equal to some constant 1. Good so far? Because remember, when you integrate 0 with respect to some variable, you get the constant of integration. Now, isolating the k, we will get c1 e to the negative quantity lambda 1 plus lambda 2 times t. And then solving the initial using the initial condition that k at 0 equals k sub 0, we will have k0 equals c1 e raised to the negative quantity lambda 1 plus lambda 2 times 0. And so k0 is going to be just equal to c1. So k at t, this is the first thing we found that we needed, is k0 times e to the negative lambda 1 plus lambda 2 times t. Cool, cool? So that's the first bit of business that we were looking to find. All right. So now we will use K at T to find A at T. All right. So dA dt equals, this is from the system, lambda 2 times K. So very similarly, to the last one, we are going to first plug in for K, all right? So we'll have dA dt is equal to lambda 2, and K at T is in the yellow there. So we're going to have K0 times e to the negative quantity lambda 1 plus lambda 2 times t. Now this is separable, right? So I'm going to have dA on the left side because there's no terms with a in it, so we don't have to get fancy. And that's equal to lambda 2 times K0 e to the negative lambda 1 plus lambda 2 times t dt. Now, the coefficient, we have got a linear function of t and the exponential, and so the coefficient of t is what I need to balance this out by, right? So I need a negative lambda 1 plus lambda 2 as a multiplier to dt. And so I need to divide by negative lambda 1 plus lambda 2, that quantity, to balance out that integral. And so integrating both sides, I'll get A is equal to negative lambda 2 times K0 over lambda 1 plus lambda 2 e to the negative lambda 1 plus lambda 2 times t plus some constant 2. Good so far? All right. Now, at time 0, there's 0 of the argon, right? Of the A at T. A at 0 is 0. So, using the initial condition that A at 0 is 0, we would have 0 equals negative lambda 2 times K0 over lambda 1 plus lambda 2. E to the negative lambda 1 plus lambda 2 times 0 plus some constant 2. So that exponential will just turn into 1. And so at the end of the day, lambda 2 times K0 over lambda 1 plus lambda 2 is equal to C2. So we get our A at T is equal to, notice that this coefficient will match, so factoring it out, we're going to have lambda 2, K0, over lambda 1 plus lambda 2 times 1 minus e to the negative lambda 1 plus lambda 2 times t. So I just plugged this stuff in for C2, and then I simplified by factoring to make it prettier. And This is solving this part. Find A at t. Cool, cool? All right, almost there. Now we will have C. We want to find dc dt. That is equal to, coming to that first one, lambda 1 times k. But in for k, right, we need to plug in k0, just like we did with A, e to the negative lambda 1 plus lambda 2 times t. dc is equal to lambda 1 times k0 times e to the negative lambda 1 plus lambda 2 times t dt. And then very similarly to last time, we have the same coefficient in front of the t. So we need a negative lambda 1 plus lambda 2. So we're going to divide by negative lambda 1 plus lambda 2 to get C equals lambda 1 times k0 over, this has a negative sign, over lambda 1 plus lambda 2 e to the negative lambda 1 plus lambda 2 times t plus some constant 3. And then using c at 0 equal to 0, we will have 0 is equal to negative lambda 1 times k0 over lambda 1 plus lambda 2 times e to the negative lambda 1 plus lambda 2 times 0 plus c3. And so you'll get a 1 for the exponential part. So c3 will be lambda 1 k0 over lambda 1 plus lambda 2, which gives us C at t equals, again, that's going to be able to be factored out. And so we will have lambda 1 k0 over lambda 1 plus lambda 2 times 1 minus e to the negative lambda 1 plus lambda 2 times t. And that was the last thing that we needed to find for that first part. Cool, cool? All right, so way up here, we found our C at t. All right, so A at t and C at t are pretty similar, but they're not the same. So it is known that lambda 1 is 4.7526 times 10 to the negative 10, and lambda 2 is 0.5874 times 10 to the negative 10. We want to find the half-life of K40. So here we go. The half-life of K40 is half of the initial, correct? So let's first find out what is lambda 1 plus lambda 2, because we have that, remember, in our denominator. So lambda 1 plus lambda 2 will be 4.7526 plus 0.5874 times 10 to the negative 10, right? If you factor that out. And that ends up being 5.34 times 10 to the negative 10. Cool so far? So if we have, remember that K at t is equal to k0 e to the negative lambda 1 plus lambda 2 times t, right? Well, we found that lambda 1 plus lambda 2 was 5.34 times 10 to the negative 10, and that's all going to be times t. Now, we're going to plug in 1/2 of k0 in for k at t because we're looking for half-life, right? So looking for half-life, we plug this in, half of the initial. That's going to be k0 e to the negative 5.34 times 10 to the negative 10 t. Well, the k0s are going to divide out to be 1. Natural log of 1/2 using properties of logs is negative natural log at 2. That's going to equal to negative, because I'm natural logging both sides, 5.34 times 10 to the negative 10t. So t is equal to 5.34 times, t will equal to, the negatives will go away, and we will have natural log at 2 divided by 5.34 times 10 to the negative 10. So this ends up being approximately, let's see, 1, 2, 3. Cool? And that, of course, would be in years. All right, so now we want to use C at T and A at T found in that first part to determine the percentage of an initial element, K0 of K40, that decays into Ca40 and the percentage that decays into argon-40 over a very long period of time. So, well, long period of time means we're going to evaluate the limit as T approaches infinity of A at T, which was equal to the limit as T approaches infinity of, so we had from A at T, that was lambda 2 times K0, right? So lambda 2 was 0.5874 times 10 to the negative 10. That's over the sum of lambda 1 plus lambda 2, which we found to be 5.34 times 10 to the negative 10 times K0, and then times e to the negative 5.34 times 10 to the negative 10 t. So, as t goes to infinity, notice that you've got this negative exponent there for t, and so we're going to end up with that exponent going to 0. So that whole exponential is going to go to what? Beautiful, 1. And then if we get the ratio of these two scientific notation terms, we end up with (0.11 times K0. So the percentage of K0 that decays into calcium 40 is 11%. And then taking the limit as t approaches infinity of C at T, well, this time we've got lambda, where was our C at T? Lambda 1 in the numerator. So we'll get the limit as t approaches infinity of Lambda 1 was 4.7526 times 10 to the negative 10. That's going to be over lambda 1 plus lambda 2, which we know is 5.34 times 10 to the negative 10 times K0 e to the negative 5.34 times 10 to the negative 10 times t. And then that turns out to be approximately 89% because the exponential goes to 1. So you get, let me write this one out, you end up getting about 0.89 times K0. And so 89% of the initial potassium 40 decays into argon 40 over a very long period of time. Cool? All right, predator-prey model. Suppose that two different species of animals interact within the same environment. Or ecosystem. And the first species, call it X, eats only vegetation. And the second species, call it Y, eats only the first species. First, assume there's no prey. Okay, then the predator species would decline in number according to dx dt is equal to negative a times x, where a is greater than 0. When the prey is present, the number of interactions between these two species per unit time is jointly proportional to their populations x at t and y at t. Thus, the predator species are added to the system at a rate of bxy, where b is greater than 0. So if you put the two rates together, we have dx dt would equal to negative ax plus b times x times y. Now, if you assume there's no predators, then the number of prey, assuming unlimited vegetation at time t, is dx dt is equal to d times y, where d is greater than 0. But when we factor in the predators, the prey population is decreased by c times x times y, where c is greater than 0. So we have dy dt would equal to d times y minus c times x times y. So if we put these equations together, we have dx dt is equal to negative ax plus b times y, which is x, this is b times x times y. And then factoring out the x, we would have negative a plus by, and dy dt would be equal to dy minus c times x times y, which is y times d minus cx, where a, b, c, and d are positive constants. This happens to be a famous system of equations called the Lotka-Volterra predator-prey model. All right, so hopefully we'll have time to look at that later in the course. We'll take a look here at this example with mixtures, or with a salt type mixture problem. So construct a mathematical model for the number of pounds of salt, x1 at t, x2 at t, and x3 at t at time t in tanks A, B, and C respectively. So with this one, you've got, pure water going into tank A at 4 gallons per minute, and this mixture coming from tank B going into A at 2 gallons per minute. And then leaving A, you've got a mixture at 6 gallons per minute. And then when you look at B, it's got that mixture leaving at 2 gallons per minute, another mixture leaving at 5 gallons per minute, and then something from C coming in at 1 gallon per minute. And then lastly, for C, you got a mixture leaving at 1 gallon per minute, a mixture coming in at 5 gallons per minute, and a mixture leaving at 4 gallons per minute. So let's take a look at what we have going on here. So if we look at x1 prime at t, that's going to be equal to, so we're looking at what's coming into tank A and leaving tank A, right? So we've got 1/100th because of the fact that A is a 100-gallon tank, right? Times what's coming in. Good. We have x2 at t is coming in, right? Because you've got stuff coming in from B. And then that is coming in at a rate of 2 gallons per minute. Good so far? And now, what's going out of A? Good. What's going out of A is 1/100th times x1 at t times 6, because of the fact that this mixture is leaving A at 6 gallons per minute. So if we simplify that, x1 prime at t would end up being 1/50th x2 at t minus 3/50ths x1 at t. Cool? So that'll be our first equation. Actually, we'll have it at the end. Now, x2 prime at t will be, so we've got x1 coming in, right, to tank B, and that's coming in at a rate of 6 gallons per minute. So we've got that 1/100th times x1 at t times 6. And then we've also got x3 coming in to tank B. So we'll have 1/100th times x3 at t, and that's just flowing at 1 gallon per minute. And then leaving tank B is 1/100th. And then we've got that mixture at 5 gallons per minute, and it's x2, right? So this is a minus x2 at t times 5 gallons per minute. Now, let's see if anything else is leaving B. Good. You've got B going into A, right? So actually, let me move this over so I have more room. And then we'll also have 1/100th times x2 at t, and then that'll be times 2. And then putting it together, x2 prime at t will be 3/50 x1 at t. I'll go to the x2's. We'll have minus 7/100 times x2 at t, putting these two together. And then we will have plus 1/100 x3 at t. And finally, x3 prime at t will be. Let's see what's going in and what's coming out. So we've got B from tank B, which has 100 gallons. So 1/100 times x2 at t times 5, because it's going into C at 5 gallons per minute. And then leaving C, we have 1/100 x3 at t times 1, because you've got C going in from tank C, you've got mixture going into tank B at 1 gallon per minute. And then you've also got mixture leaving from tank C, its own mixture, times 4. And so x3 prime at t would be 1/20 x2 at t minus 1/20, sorry about the dogs, times x3 at t. And so our system would be the three of them together. It would be this one here, this one here, and this one here would be our simplified system. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And if you like what I'm doing, hey, click that like button and please subscribe. Bye.